We'll start in about a minute. Today we'll look at more problems from section 11.8 on power series. We started this problem yesterday, so we'll just start it over again. We want to find all of the values of x for which this infinite series converges. So one common approach is to use the ratio test. So we'll do that one. We'll use the ratio test for this one. So that involves taking the limit as n approaches infinity of the absolute value of the n plus first term from the series divided by the nth term. Okay, so on this one, well, the nth term is, the n plus first term is negative 2x to the n plus 1 divided by the square root of n plus 1 plus 3, or the square root of n plus 4. And when we divide this by the nth term, that's equivalent to multiplying by the reciprocal of the nth term. So this is the nth term. The reciprocal of this is the square root of n plus 3 over the quantity negative 2x to the n. So if there's any confusion about what I just did, we've done it before, but let me know if you need further explanation on that step. So we'll simplify what's inside the square roots, inside the absolute values, I mean. So let's move the square root of n plus 3 and put it over the square root of n plus 4 and write it as a single square root of n plus 3 over n plus 4. It's using the quotient property of radicals to do that. And then another thing we can do, the expression negative 2x to the n plus 1 divided by negative 2x to the n just simplifies to negative 2x to the first, or negative 2x. Okay, if we take the limit of this, the limit of the square root of n plus 3 over n plus 4 is, as n approaches infinity, is 1. And so the limit of this is just the absolute value of negative 2x. Right, x just represents a real number. And so this limit is equal to negative 2x. So we want this limit, negative 2x, the absolute value of negative 2x, which is just 2 times the absolute value of x, right? And so 2 times the absolute value of x, we want that to be less than 1. So this simplifies to the absolute value of x is less than 1/2. And then to solve this absolute value inequality, we remove the absolute value symbols, and the absolute value of x less than 1/2 is equivalent to negative 1/2 less than x, which is less than 1/2. Okay, so this is the open interval for the values of x for which this infinite series converges. But we have to test the endpoints to see if the infinite series converges at either of the 2 endpoints. The reason that we cannot include the endpoints using this process is for what reason?
Because at those endpoints will be equal to 1 and they'll diverge.
Yeah, so if we replace x with either negative 1/2 or 1/2, the limit of the ratio is equal to positive 1, and the ratio test is inconclusive when the limit is equal to 1. So we have to test the endpoints separately to see if they will be part of the interval of convergence. So first, let's test negative 1/2. In the original series, just replace x with negative 1/2. So negative 2 times negative 1/2 is positive 1 to the n, and 1 to the n is always 1. So we're testing this series 1 over the square root of n plus 3. Okay, and we know what happens with this series. It diverges. If we do a limit comparison test with 1 over the square root of n, which we know diverges, you can show this by comparing. To be more explicit, I'm thinking of the limit comparison test by limit comparing the infinite series of 1 over the square root of n. So 1 over the square root of n is a p series. This is like 1 over n to the 1/2. The value of p is 1/2. So this series diverges. So we're going to exclude negative 1/2 from the interval of convergence. Then we test the other endpoint, x equals positive 1/2. So this time, when we were in the original series, when you replace x with positive 1/2, negative 2 times 1/2 is negative 1. So this time we do get an alternating series, negative 1 to the n divided by the square root of n plus 3. So this one, the alternating series test applies. If we use the letter b sub n, if our b sub n terms are 1 over the square root of n plus 3, it's pretty easy to show that the series decreases as n gets larger. So this is, it satisfies the first condition of the alternating series test. So we're applying the alternating series test to this. So that sequence of numbers is decreasing. That's the first step, and then, or the first requirement. And then the second one is that the limit of those terms equals 0. So that's the second requirement of the alternating series test. So that means we do include 1/2 in the interval of convergence. Okay, so for the given series, the interval of convergence, let's see, we're excluding -1/2. So it's in interval notation, parenthesis, -1/2, comma, 1/2, bracket. This is the interval of convergence for that infinite series. The radius of convergence is just 1/2 the length of that interval. So the length of the interval is 1, so the radius of convergence is 1/2. Okay, the next one. The infinite series, the terms are x minus 5 to the n times n factorial divided by 5 to the n as n ranges from 0 to infinity.
Ratio test?
Yeah, I'm thinking the ratio test. I decided I wanted to investigate the nth root of n factorial. I want to see if I can come up with an answer before looking it up. Because maybe, I don't know, I'm just thinking, maybe we can use the root test if I find an answer to the nth root of n factorial. But until then, we'll just use the ratio test for this one. Okay, so let's use the ratio test. Okay, so the limit as n approaches infinity of the absolute value of the n plus first term divided by the nth term, or equivalently, the product of the n plus first term and the reciprocal of the nth term. Okay, the n plus first term is x minus 5 to the n plus 1 times n plus 1 factorial divided by 5 to the n plus 1. Then we multiply that by the reciprocal of the nth term. So the nth term is just the term that we're looking at in the series. So the reciprocal of that is 5 to the n over the quantity x minus 5 to the n times n factorial. Okay, then we'll simplify a bunch of things. So if I skip too many steps, let me know and I'll explain in more detail. First of all, let's focus on the binomial x minus 5 raised to the n plus first in the numerator. We're dividing that by the binomial x minus 5 to the nth in the denominator. So what will that simplify to?
X minus 5.
Yeah, x minus 5 to the first in the numerator. Yeah. So in the numerator, we'll just get x minus 5, by which we mean x minus 5 quantity to the first, but we don't need to write it. We should put it in parentheses, though, for now. Okay, so that takes care of those terms. And then what?
So the 5 to the n cancels out the 5n plus 1, so we're just left with 5 to the first in the denominator.
Yeah. 5 to the n divided by 5 to the n plus 1 simplifies to 1 over 5, or just a factor of 5 in the denominator. Okay, so that takes care of 5 to the n divided by 5 to the n plus 1. And then what about n plus 1 factorial divided by n factorial?
Would it just be n plus 1?
Yeah, that should just leave n plus 1 to the first power in the numerator.
Yeah, n plus 1 factorial divided by n factorial simplifies to n plus, a factor of n plus 1 in the numerator. So n plus 1 in the numerator. Okay, so now we're basically ready to compute the limit. So if x is a real number, if you just pick x to be any real number and fix it, and then compute the limit, what will the limit be equal to?
Infinity.
Yeah, infinity, except for one value of x.
5?
Yeah, when x is 5, the limit is 0. But for any other value of x, the limit is infinity. So this limit equals 0 for x equals 5 only. Otherwise, the limit is infinite. Or I should say the limit diverges to infinity. Okay, so there's only one value of x for which this infinite series converges.
Sure enough, that satisfies the first possibility of the power series theorem, so that makes sense.
What's that?
So sure, just looking at our notes, sure enough, that satisfies the first possibility of the power series theorem we discussed last class, where the series converges only when x equals a, where a in this case
Yeah.
is 5.
Right. Yep. Yeah, that's one of the three possibilities. Yeah, but when x is 5, all of the terms are 0. So not a very exciting infinite series, but we would just say x equals 5 is the interval of convergence. It just consists of one number in this case. Okay, let's move on to the next page. So let's try the ratio test. So the limit as n approaches infinity of the absolute value of the n plus first term divided by the nth term. So just in case it helps, so if we take the absolute value of the n plus first term divided by the nth term, that's equivalent to multiplying the n plus first term times the reciprocal of the nth term, which is 1 over a sub n. So those are obviously the same, but okay, so the n plus first term is x minus 2 to the n plus 1 over, so what should I write in the denominator?
Quantity n plus 1 squared plus 1.
Right, the quantity n plus 1 squared plus 1. And then we multiply by the reciprocal of the nth term, so this is the nth term. And the reciprocal is n to the second plus 1 over x minus 2 to the n. Okay, so just like we've been doing, first let's write the n to the second plus 1, and then the quantity n plus 1 squared plus 1 is n to the second plus 2n plus 2. And then we simplify x minus 2 to the n plus 1 over x minus 2 to the n. So we just get x minus 2 to the first in the numerator. And now we can compute the limit. We know what the limit of n to the second plus 1 over n to the second plus 2n plus 2 is. It's equal to 1. And so this limit is the absolute value of x minus 2. For every fixed value of x, x minus 2 is unaffected by n. So is there a question about why the limit of n squared plus 1 over n squared plus 2n plus 2 is 1? Okay, so the limit is the absolute value of x minus 2. And since we're using the ratio test, this will converge for the absolute value of x minus 2 is less than 1. So we solve this inequality. We remove the absolute value symbols, and we get negative 1 is less than x minus 2, which is less than positive 1. Then add 2 to all three parts. We get 1 is less than x, which is less than 3. Okay, so the radius of convergence is how much?
3.
The radius of convergence is 1. Is that what you said? So the length of that interval, even though the endpoints are not included, the length is 2. 3 minus 1 is 2. So half of that is the radius of convergence. And then the interval of convergence will at least be the numbers strictly between 1 and 3, but we might also include the endpoints or not. We have to test the endpoints. So let's test the endpoint x equals 1 in the original series. So when we replace x with 1, 1 minus 2 is negative 1, so we get an alternating series, negative 1 to the n, divided by n to the second plus 1. So we pretty much know what's going to happen if we use the alternating series test. We know whether or not both conditions are satisfied just by looking, don't we? Both conditions are satisfied. So if b sub n is 1 over n squared plus 1, the next term is smaller because the denominator will get bigger. So this will be greater than b sub n plus 1, which is 1 over n plus 1 squared plus 1. So the b sub n sequence is decreasing, and the limit of the b sub n sequence goes to 0, right? So the limit of 1 over n to the second plus 1 equals 0. So both conditions are satisfied at the endpoint x equals 1. Okay, then test the other endpoint. The other endpoint is x equals 3. So in the original series, replace x with 3. 3 minus 2 is 1. 1 to the n is just 1. So we get 1 over n to the second plus 1. Okay, so what do we know about this infinite series?
It goes to 0.
It does converge. 1 over n to the second plus 1 reminds me of 1 over n to the second. So if I were to do a limit comparison with the infinite series 1 over n to the second, which I know converges, then I would be able to get a limit that's equal to a finite positive number. So we should know that this converges, but let's go ahead and do a limit comparison test. With the series 1 over n to the second. So we know that this series converges because it's a p series. The value of p is 2, which is greater than 1, so this converges. So remember what the limit comparison test says. Okay, so if this is my sequence of a sub n terms, and I want to compare it with this series, which is, refer to this as the limit of the b sub n terms. And if the limit of a sub n divided by b sub n is equal to a finite positive number, then both series do the same thing. Both series will converge or diverge, but since we know that this one converges, if after applying the limit comparison test, we get a finite positive number for the limit, then we will know that this one also converges. So this C has to be positive and finite. Okay, so the limit of a sub n divided by b sub n, so 1 over n to the second plus 1 divided by 1 over n to the second. So we'll simplify that and write it as n to the second over n to the second plus 1. What's that limit equal to? Positive 1. So positive 1 is a positive finite number. So by the limit comparison test, this series does the same thing as this series of the 1 over n to the second. So we know that this one converges, so this one also has to converge. Okay, but that's just one of the endpoints. Both endpoints are included. So the interval of convergence for this series is the closed interval from 1 to 3. So I'll write that in here somewhere. The interval of convergence is from 1 to 3 for this series. Okay, if there's anything that you need explained, let me know. I know there's a lot of writing scrunched up into a small space, but let's go on to the next problem. The infinite series, the terms are n factorial times the binomial 2x minus 1 to the power n, as n ranges from 1 to infinity. So let's use the ratio test. We want to find all values of x for which this series converges. The limit as n approaches infinity. Well, this time we don't have a rational expression, so it's not going to be too bad. The n plus first term is n plus 1 factorial times 2x minus 1 to the n plus 1 divided by the nth term, which is n factorial, divided by 2x minus 1 to the n. Okay, so we simplify. Okay, so when we simplify n plus 1 factorial divided by n factorial, we just get n plus 1. And the binomial 2x minus 1 to the n plus 1 divided by the same binomial 2x minus 1 to the nth, we just get 2x minus 1 to the first. Okay, so for values of x that are not equal to 1/2, the limit is infinity, and the limit is 0 only when x equals 1/2. So this limit is equal to 0 when x equals positive 1/2. Otherwise, the limit diverges to infinity. So this series converges at one value, x equals 1/2. Did I say that right? The infinite series converges at x equals 1/2. Okay, the next one the infinite series, the terms are x to the n divided by 1 times 3 times 5 and so on times 2n minus 1. N ranges from 1 to infinity. We want to find all values of x for which this series converges. So let's use the ratio test again. So the limit of the n plus first term divided by the nth term. So the n plus first term is x to the n plus 1 over 1 times 3 times 5 dot 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 2n minus 1. What comes after 2n minus 1?
2n.
Okay, if down here, if you replace n with n plus 1, you get 2 times n plus 2 minus 1.
2n plus 1.
Yeah, so this factor is 2n plus 1. And then we divide that by the nth term, which is x to the nth, over 1 times 3 times 5, dot, dot, dot. Last term, 2n minus 1. Hey, this is going to simplify pretty nicely. Hey, I can write more detail if you want, or I'll just start out by explaining. If we multiply the rational expression in the numerator by the reciprocal of the rational expression from the denominator, we're going to get x to the n plus 1 divided by x to the n, which simplifies to x in the numerator. And then we're going to also have 1 times 3 times 5 dot 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 times 2n minus 1 divided by 1 times 3 times 5 dot 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 times 2n minus 1 times 2n plus 1. So all of the factors cancel except the binomial 2n plus 1, which is in the denominator. So holler if you want more detail on that. Okay, so for any real number x, if I just pick any real number whatsoever, what's the value of the limit? So just think of going through the process of picking x to be a real number one at a time, and then computing that limit.
0.
0, yeah. So this limit is equal to 0 for all real values of x. And since 0 is less than 1 by the ratio test, this infinite series converges for all real numbers. So the interval of convergence is from negative infinity to infinity. And the radius of convergence?
Infinity.
Infinity, yeah. Might as well throw that in, radius of convergence. Hey, the next one,
Root test.
we could use the root test. The ratio test works, but we can try the root test just for a little bit of variety. So the root test, we compute the limit as n approaches infinity of the nth root of the absolute value of the nth term. So if this limit is less than 1, then the series converges. So we want to find the values of x for which this series converges. So the limit as n approaches infinity of the nth root of the absolute value of x minus 5 to the n over n So what do we write next? Yeah.
The absolute value of x minus 5.
Yeah, in the numerator, we'll just have the absolute value of x minus 5. The nth root of x minus 5 to the nth is just the absolute value of x minus 5. And in the denominator, we have the nth root of n, or n to the 1 over n. So now we can compute the limit for each value of x. It's unaffected by what n does, but what does n to the 1 over n go to?
1.
Goes to 1. So the limit of this is the absolute value of x minus 5. So using the root test, we set the absolute value of x minus 5 less than 1, and that will tell us what the open interval for convergence is. So we want this to be less than 1. So if the absolute value of x minus 5 is less than 1, then without absolute value symbols, we have -1 less than x minus 5, which is less than 1. Then add 5 to all three parts, and we get 4 is less than x, which is less than 6. The radius of convergence is 1. The length of that interval is 2. 6 minus 4 is 2. But then we have to determine if the endpoints are included or excluded. So this one won't be too bad. So let's test the endpoint x equals 4. In the original series, replace x with 4, we get 4 minus 5 to the n, or -1 to the n, divided by n. So what does this series do? Does this series converge or diverge?
Diverge.
Did you say diverge? No. This is the alternating harmonic series which converges. In fact, you can use the alternating series test to show that this one converges. So you can just remember or use the alternating series test. What was I going to write? The alternating harmonic series converges so you can remember that, or as I said, you can use the alternating series test. The terms 1 over n decrease as n approaches infinity, right? So that's the first condition of the alternating series test. And then the limit of 1 over n as n approaches infinity is 0. So this converges. The other endpoint 6, test x equals 6, replace x in the original series with 6. 6 minus 5 is 1. 1 to the n is 1. So we get this series, the terms are 1 over n. Do we know anything about this one? Yeah, it diverges. This is the harmonic series. So always remember the harmonic series diverges. And the alternating harmonic series converges. Okay, so we're going to exclude 6 from the interval of convergence, and we're going to include 4. So include 4 and exclude 6. So our series, the interval of convergence is bracket 4 comma 6 parenthesis. It's the interval of convergence. Okay, there's less than 2 minutes. We can at least look at this one, start looking at this one. Now you could use the root test or the ratio test. let's start out with the ratio test, and then we'll quit when it's time in a few seconds. So the n plus first term, x plus 2 to the n plus 1, divided by n plus 1 plus 2, which is n plus 3, times 2 to the n plus 1, multiplied by the reciprocal of the nth term. So the nth term, the reciprocal is n plus 2 times 2 to the n over x plus 2 to the n. Then simplify a little bit. X plus 2 to the n plus 1 over x plus 2 to the n is x plus 2. We're out of time, so on Friday we'll start section 9 in chapter 11.